Hello, we will have a look at the phenomenon of convection and diffusion. Um, at first, I want to introduce, if you want to design an airplane, the fluid flow behind the airplane is really interesting, and it is also really mysterious a little bit. Here you can see a jet, an airplane, and normally the swirls and the convective flow behind the airplane is invisible, you cannot see it, but here in this case the airplane flies over a layer of clouds, and that's why you can see really good swirls, swirls that were built here on the wings. And you see the airplane here has no winglets, so you will generate a lot of swirls behind the wings. This is a really serious problem, and the design of the winglets is a it's a good feature to prevent swirls after the airplanes. And when you do your exercises with your own airplanes, you will realize that you can generate a lot of swirls behind the wings. And this is a really it's a case and it's a design of the Boeing 737 MAX 8, and maybe you've heard of this airplane. It is a really good and modern airplane. The idea was to design a really an airplane that saves energy, an airplane with a lot of fluid dynamic features. For example, you see the turbine here at the right side. It is a really big turbine. It is much bigger than other turbine designs before. And so the engineers had to decide to place it a bit in front of the wings, a bit more, not directly under the wing. The design was made to place it a little bit before the wing. And the airplane here, the turbine of the 737 MAX, was also a really modern design. It has a really big area where the air can enter the turbine, and it has really big wing areas, so it can save a lot of energy, and it is also not so loud. But the disadvantage was it has to be built a little bit bigger than normal turbines. So they had the problems here with this 737 MAX that the turbine of the airplane had to be there was not enough space to put it directly under the wing. They had to place it a little bit before the wing. And because of this effect, sometimes there was the danger of a stall effect. There was a little bit danger that the nose of the airplane could be shifted upwards a bit. And now you get the problem if you have if the angle of attack is too high. If the angle of attack is higher than 14 degrees, you get this kind of stall effect. And that's something we examined in the last exercise, the stall effects. Normally, if you have a CFD code, if you have a standard turbulence model, you can't see this effect really well. Yeah, you can't realize the stall effects because and the CFD will predict the stall not so much. Yeah, it depends on the turbulence model. This prediction of stall is really complicated, and normally a normal CFD code will calculate much higher forces. But in reality, we have the stall effect. In reality, we have this high turbulence, fluid flow, and this will cause a high decrease of forces, of the lift forces and the wing. And this is, of course, not good for the airplane. So here at this example they tried to do an electronic software correction function to prevent these stall effects, and they put also pressure sensors on the upside of the wing, and if the pressure sensor detects stall effects, if they detect a pressure rise, the software function can act and it can push down the nose again to get more lift forces in the wings. But so this software function acts more or less alone. It is a bit difficult for the pilots to switch it off, and so this software function called Maneuvering Characterized Augmented System, MCAS, was able to act autonomously, and it pushes down the nose to get more lift force at the wings. But then they occurred a problem. Maybe you know it from the news, know it from the newspapers, that Boeing had a problem with the sensors, and the sensors did not really detect this pressure drop really good. So the software function was not able to work, and it tried to push down the nose always, even if the angle of attack is not over 15 degrees, and so to really big accidents happened with this model. Okay, so you see turbulence and the prediction of swirls with CFD is really important, that we can predict it in a good quality to prevent this stall effects. I also showed you the measurement of the stall effects on our model airplanes. Okay, and here let's have a look at the turbulence and at the effects of high turbulence and low turbulence. You already learned the so-called Reynolds number, and relatively low Reynolds numbers gives us more swirls, more eddies. This is a picture of a jet of gas, and if you get higher Reynolds numbers, you can get them by high velocities or lower viscosities of the fluid, and then you get more smaller swirls. So in general, we can say we have if you have a jet turbine, or if you have a nozzle, if we inject the gas or any kind of fluid or even water, it's the same effect. We have a kind of convective flow. Convective flow is always the flow in the direction of the jet. If you imagine we have an airplane turbine, and if we have a jet after this turbine, this is a convective flow. But as you can imagine, jets in nature, they always will have so-called diffusive flow, and the diffusive flow is always in the it's also in a vertical direction here. If you have convective flow in a horizontal direction, we will have this diffusive flow in an angle to 90 degrees to this convective flow, and the fluid will also flow to the sides, to the kind of diffusive flow, and there will also occur these eddies and swirls, and these eddies and swirls, they will produce this diffusive flow behavior. So if we maybe have a velocity of 10 meters per second here at the nozzle exit, this component of the velocity will be lower and lower after some time, but there will occur also a velocity in this diffusive direction here. Okay, so we will produce, if you look closely at the jets, we will always produce a core boundary and a boundary layer that is built from the swirls, and that's what we can see if we look at the jets. Okay, maybe here is some good visualization of this effect. That was a nitrogen jet, a gas jet, and I made measurements for this gas jet, and I also did some and the CFX, some large eddy simulation. And if you use large eddy simulation, you can predict turbulence swirls really good. Normally we don't use this large eddy simulations. Normally we use K epsilon or K omega models or SST models, and the prediction of these swirls with the SST model, turbulence model, is not so good. If we use here this kind of large eddy simulation for the turbulence prediction and the swirl prediction, the quality of the prediction is much better. So maybe if you design your airplane, if you estimate the production of swirls over the wings, a large eddy prediction is much more reliable and much better than SST prediction. But of course we never use the large eddy simulation because it's a bit more complicated to make this kind of simulations. Here in this module we only want to do SST or K omega or K epsilon simulations. So, and additional to the CFD simulations of the nitrogen jet, I did some experiments in our Schlieren chamber, and it was also the injection of nitrogen into the chamber, and we made movies with our Schlieren camera, and so we were able to visualize the jets really good. And we even had some supersonic areas in this jet, and it was possible to visualize. And if you look now at different time steps of the simulation and we compare it with different time steps of our Schlieren jets, you can see that the large eddy model will be quite realistic prediction. If we compare this with the other turbulence models, we will never have such good quality in the prediction. Okay, so you've learned we have convective flow, that's what we normally learn at school or in the low grade classes, and we will also have additional to this convective flow a diffusive flow, and the diffusive flow is built by the turbulence and the swirl, and more or less it is described by a diffusion coefficient. And so let's have a small look, and I put this sentence, this very famous sentence of Mr. Richardson, to my slides. You can see it is called big worlds will have little worlds which feed on the velocity, and little worlds will have lesser worlds, and so on up to viscosity in the molecular sense. So our effect of diffusion, our effect of turbulence is also connected to the effect of viscosity. And if we use easy models like SST models or K epsilon models, the swirls are modeled with a kind of turbulent viscosity. Of course, that's not a really detailed description of physics, but more or less this swirl, this chaotic behavior of the fluid can be described by an overall turbulent viscosity. Of course, with this model you cannot predict any stall effect on an airplane wing, but more or less you can describe the amount of energy that is in these swirls. And yeah, this picture is also a really famous picture. I have not cited it, but it's taken from a sketch of Leonardo da Vinci. Leonardo da Vinci was really interesting in fluid flow problems, and he was also interested in building airplanes, yeah, even in this time. And he was also interested in turbulence. And of course, he had no camera or no photo, but he looked really close at the turbulence and tried to paint it, and it looks like art to me, but it had a technical, physical sense. Yeah, he tried to invent machines for this effects. Yeah? Hydraulic machines or airplanes also. That's why he was interested in turbulent behavior. And if you look closely at this picture, it's not chaotic. You can see some natural effects here. Okay, but of course nowadays it's much easier for us. We can take a photo, we can film it with our video camera and get an impression of the swirls. Okay, but let's go back to computational fluid dynamics. We want to try to predict convective. That's not so difficult, but now in this lecture I want to explain you how to predict also diffusive flows.